Welcome to week 2, and we're going to be talking more about bonding this week as promised. We're going to be looking at 2 theories. The first one is valence bond theory. So if you're watching this video, that's one we're going to talk about right now. Our polar bear is here. We'll get to him in a little bit. But this theory, valence bond theory, is based off Linus Pauling's picture is on your notes. As I mentioned, he's one of my heroes. He won 2 Nobel Prizes, and the one had to do with his ideas on chemical bonding, which has helped us to progress. He won a Nobel Prize in 1954 for that, and yeah, it wasn't that long ago. 70 years ago. I know some of you think that's so long ago, but we've come a long way. In the picture, he's holding up, I don't know if I hold it up for those who can't see it, he's holding up these big molecules and stuff. Like I have my little ones that I made, which you guys would have gotten to make if you were here. But when my first day, I remember walking into the biochemistry building at Duke when I went to graduate school, and there was, in the lobby, these gigantic molecules of proteins and stuff made. And I'm not that old, but that was like 30 years ago. And so it was before we had all this computer imaging that we can do now. And so they would make these models to be able to look at them and see them in 3 dimensions. And that was built off of these theories that we're going to look at. So valence bond theory talks about how orbitals overlap. Both theories actually are looking at how orbitals overlap between atoms. And this theory helped to explain where that 109 degrees came from, the tetrahedral. How do we get 109? And the reason that's a question is, if you go back to 221 when you learned about electron orbitals, we talked about S's and P orbitals. So S orbitals were just spherical. So we can skip down here a little bit. So if you think about it, a sigma bond, there's 2 types of bonds in the theories. Sigma bond is what most of us think about, and that is that atoms have an overlap between the nuclei. So the overlap of the orbitals is between the nuclei. And so when most of the bonds we represent them as sigma bonds. So here would be the black is my carbon and the white is hydrogen. And this would be representing a sigma bond. And if I made this smaller, we would see more of the overlap, which would be more representative. A pi bond, though, is another possibility. You can also have, if you remember, p orbitals have this infinity sign look to them. And so we would see the overlap again. So this would be a sigma bond because the overlap is in between. So I'm going to skip around these questions a little bit. So the question is, where's the 109 degree come from? Because this overlap should be making things linear. Or if you had carbon, let's talk about the 4 bonds first, and I'll come back to this. So carbon's 1s2, 2s2, 2p2. So if we look at the 2p2, remember p's had 3 orbitals. We would have 2 unpaired electrons. The 2 s's would be paired up. And where do we get 4 bonds from? And so that's what Linus Pauling went about to explain. Also, if we remember, p orbitals make this infinity sign along the 3 axes. So along the x-axis, the y-axis, and the z-axis. So if we go along the x, the y, and the z, then our overlap should always be 90 degrees because the 3 axes are 90 degrees apart. So how do we get this tetrahedral where it's 109 degrees? Why? How did it morph things out? And that's what Linus Pauling came up with. He said that these orbitals, the 2 s's and the 2 p's, all come together and they hybridize. And so he made hybrid orbitals. So the 2s and the 2p, and actually if I represent it a little bit better, the 2p is actually higher energy than the 2s, right? So we fill in the 2s first, and then we start filling in the 2p. So what he said is these 4 orbitals, the 1 2s orbital and the 3 2p orbitals, all hybridize, and they make 4 equivalent orbitals. So these are all equal in their energy, and etc. And he called this hybridized orbital sp3. So we hybridized an s with a p, and the superscript 3 is that there's 3 p orbitals that we hybridized. There would be a superscript 1 for the s, so s1p3, except we always leave ones out. So these are sp3 orbitals, and they're all equivalent. And these 4 electrons would then put 1 into each one. And so now we have 4 unpaired electrons, and that is why carbon makes 4 bonds. And so when you get to those 4, that's where also the sp3 is where the tetrahedral comes from. And so that's what my examples there are at the bottom of the page. Before we move to those examples, though, let's talk about pi orbitals. Pi orbitals, sigma is the orbitals overlapping between the nuclei. A pi orbital is when the overlap is above and below. And this is where I am missing all of you. I'm missing all of you desperately anyway, but usually I will have somebody in here who was a clown or something and can make balloon animals, and so we can make balloon orbitals. So if somebody is really good, or you want to like learn how to do that in your time at home, you can do it. And if you make, you can do it with these are p orbitals along the y-axis. And what happens, so we have an overlap in between already with the ones along the x-axis. For these to overlap, they're going to actually morph. And we get this overlap. Remember, we're drawing this as if it's material, but electrons really behave as energy. But the overlap is above and below, so it's kind of make it donut. These would be the nuclei here. And so the electrons are in this area. They're occupying this area above and below. That is 1 pi bond. And so the overlap is above and below. Now in the valence bond theory, you always start with sigma. So you would have a sigma bond that would be in between, so let's just say sigma, in which the overlap would be in between the nuclei. And then you get this pi bond. Now, this is a double bond that I have drawn here with my amazing artistic skills. I know you dear students are all saying, no, that is not a double bond. That looks like a triple bond. I was going to get my example there. So a single bond is just overlap in between the nuclei, 2 electrons. A double bond is now one is overlapping in between, and the second set of electrons is above and below. That is 1 bond, this donut. A triple bond, the overlap is in front and behind. So we'd have to go along the z-axis, the p orbitals, and they would overlap. And so you get this beautiful picture. I think I have a picture of it on the second page, and the book that I posted for you does. And yeah, you can kind of look at them, or you can also Google. Some people can see it better than others in their mind. So a pi bond is that overlap above and below. This definition for sigma and pi is true for both theories that we're going to walk through today or this week. All right, just thinking where I want to go with this. We're going to look at orbital overlaps. So I have an example on your page of CH4. So what would happen is, remember we had our 2s and our 2p's, so this is carbon. So we have 4 electrons total, and these overlap into the sp3. So they're all equal, and so now what can happen is the carbon now has these 4 equal, and it can make the CH4, which would be a tetrahedral, so these 3 would be coming down. If you look at nitrogen, we have the same idea. Now we're going to have 5 electrons, valence electrons. The inner ones, the 1s, are core electrons. So we have 2 electrons in the 2s, and nitrogen has 3 electrons in the 2p. These are going to hybridize again into our sp3, The sp3 hybrid orbitals have an energy that's in between the s's and the p's. Now there's only 4 total because we only had 4 orbitals to start with. That is something that is true in both theories that we'll go through, that the number of atomic orbitals, so these are atomic orbitals when we were just dealing with nitrogen, the number of atomic orbitals will still be the same. We can't create new orbitals, a new number of orbitals. We did hybridize them. So now we have 5 electrons. So each one will get 1, and then the 5th one will be there. So we have this pair of electrons. And so when we draw NH3, NH3 has 8 electrons. Well, the hydrogens, so this would be 1 unpaired electron from nitrogen. And then those 2 that are paired up there, those would be these 2 unpaired electrons that we are famous. The other electron from each of these hydrogen bonds with the nitrogen is, of course, coming from the hydrogen. So each of these would be 3 sigma bonds overlapping. And then we have this unpaired. So this is an unpaired electron. I'm sorry, not unpaired. This is a lone electron pair. I've been thinking about free radicals because I think that shows up on the next page. So I can give you a little talk about free radicals, maybe not. And let's do the last one on this page, H2O. So if we look at oxygen, oxygen has 6 valence electrons. So we would normally show it as 2s2 and then 2p4. So when we hybridize, again, this part always students, I can see you all out there, all my students from the past 20-some years, giving me these puzzled looks. But as we go to the next page and as you do examples, you become very proficient with this. All right, so we would have sp3 as the name, and we have 6 total electrons. So 1, 2, 3, 4, they each get 1, and we would have 2 lone pair of electrons on oxygen. And indeed, when we draw water, we draw it with the Mickey Mouse arrows. And so those 2 paired of electrons that are just on oxygen are coming from that. All right. Also, if you have the notes, that first page in the middle, it has these nice pictures, and it's trying to show you the pi bond. So the pi bond, the next page actually shows a much nicer picture. So let's move to the next page, and we can actually move. Let's clean our board. We're going to make a chart. So the hybrid orbitals always have to do with the Vesper geometry. So if we talk about our clouds around the center, we got the possibility of 2, 3, 4, 5, or 6. And so we had a name for each one of these. So valence shell electron pair repulsion geometry. The answer is going to come out, this is based off the Vesper. We'll look at the bond angle. And we'll also look at the hybridization. So when there were 2 clouds around the center, so like in CO2 would be our example, we end up with a double bond. I won't draw all these out. But we come out that we say that is linear. And maybe you remember, but you'll have a nice chart. 180 degrees, that was supposed to say bond angle. And the hybridization, well, only 2 things have to hybridize for the carbon. So the carbon just has to hybridize with something on each side. And I have an example as we go down to show you this. But we call it an SP. So when you have only 2 clouds around you, you only need 2 orbitals to hybridize. Always S hybridizes first, and then P. So SP, That gives us 2. All right, when we get to 3, we're going to say sp2. So the S hybridizes gives us our first thing that hybridizes, and then 2 of the P's hybridize, and that gives us 3. And this was called the planar triangle, or trigonal planar, if you like to talk that way. And our example was our SO3 or SO2. So we will see we have double bonds in these. So SO3 will be our example. And I'm going to go ahead and draw it because that is going to become important for our next step. All right, 4CH4, H2O, the ones we just did, that's a tetrahedral, 109-ish degrees. Again, if you want more precision, that's wonderful. All right, so sp3. So there's 4 things that hybridize. Tetra means 4. S is the first thing, and then all 3 p orbitals. So when we get to 5, we cannot just say, it's not this simple, we can't just say sp4, because there are not 4 p orbitals. So to get to 5, we say sp3, so s, 3 p's, and then we bring a d in. Just 1d orbital hybridizes. So this was, I have my example over here. Yeah, this was this beautiful picture. So we have a tetrahedral above and a tetrahedral down below. So there was a triangle in the middle, and so it is called a triangle bipyramid. Interesting enough, right after I did my video the other day, I was listening to a meditation on the way home, and she talked about the diamond tetrahedrals. And so it's a double tetrahedral, which is what this is, a tetrahedral on top of another one, so we have a triangle base. But if you looked at the face, because you have these 2 triangle faces that come together, they kept calling it a diamond tetrahedral, and I was like, oh, that is such a lovely thought. An example would be PF5, I think was the example we did the other day. And the bond angles, just to review, our bond angles in the triangle would be 120, because that triangle is planar triangle, and then the top and the bottom would be 90 degrees, so 120, 90 degrees. All right, and then our last one is the octahedral, and I don't know where I put it, but an octahedral is a square. We'd have a square pyramid, and then something above and something below. And all these angles were 90. So maybe some of you already answered where we're going with this. The S hybridizes, oops, 3 P's hybridize, and then 2 D's are going to hybridize. So we have an S, 3 P's, and then 2 D's, and that does make 6. So in the past, my students were not allowed a calculator for the first 4 weeks of the term, so you did have to use your fingers to count. So you can try that challenge and see if you can do all this without a calculator and with your brain cells, and everything was closed book. All right, so this little chart will be handy, and last week our notes actually had a place where you could fill in the hybridization. So you can, if you want, go back and fill in those notes, and it actually goes perfectly with the Vesper geometry. I'm looking at what's next on the page, so those of you who do have your notes up, C2H4 wants us to look at that. Oh, actually, before we go there, I did want to talk about sigma and pi bonds. And actually, I want to add one more thing to our chart, and that is unhybridized orbitals. So specifically the p orbitals. So for sp3, our tetrahedral, there's 0. No unhybridized orbitals. The S's and all 3 P's hybridized and are all equivalent. But you can see in our first 2, there's 3 P orbitals. When we make the sp, there's still 2 unhybridized P orbitals. They're still in their original 90-degree along the y-axis and z-axis. And so these are going to be the ones that make the pi bonds. This is where pi bonds come from. And it's a question on the middle of the page. It's actually the next question. I'm so glad you asked. Pi bonds, unhybridized p orbitals, make a pi bond. And by the way, it is a capital pi, although you can make it an apple pie, a cherry pie, whatever kind of pie you want. Or you can make it the squiggly pie like we make in math class. All right, and the sp2 makes one unhybridized. So a pi bond is when you have a double bond. So if we look at our SO3 over here, our SO3, we are going to count sigma and pi bonds, which we're going to do a whole page of practice with this. We have 3 sigma bonds. So a double bond is 1 sigma and 1 pi. So we have 3 sigma and 1 pi bond. So this double bond is 1 sigma, 1 pi, and the singles are always sigma. So we look at for the CO2, we have 2 sigma and 2 pi bonds. And there is a picture trying to show you that in C2H4 was my other example. C2H4 is going to end up being an sp2. So the carbons would double bond and the hydrogens would be attached. Carbons make 4 bonds. It's a wonderful way to make yourself look really smart, like you can draw these fast. We're going to do some organic chemistry in lab this week, and so you'll all get more proficient. I don't expect that I can teach you a whole year's or a lifetime worth of organic chemistry in 2 hours or less, but to give you a better appreciation of drawing carbons. But what happens here is this carbon, if you look at the carbon and you just look at one carbon at a time, the carbon has 3 things around it. So these carbons are planar triangle, 120 degrees. And now you're going to also be asked, what's the hybridization? And the hybridization is sp2. So last week, the first week was about becoming proficient at drawing Lewis structures and becoming familiar with them and some of the other little nuances like bond energy and stuff with bonding. And this week we're taking it one step further to see the idea of where these words came from. And then we're going to add one more piece with this. So how many sigma and how many pi bonds? Well, the pi bond's easy. You just look for a double. So I have 1 pi bond and I have 5 sigma. So the hydrogens are each a sigma, and then a double bond is 1 sigma and 1 pi. So this total has to equal the total number of bonds. We have 6 total bonds, 5 are sigma and 1 is a pi. And it makes sense. We can have a double bond because those carbons have an unhybridized orbital. All right, let's do the next one, which was CH2O. I'll go over here. So CH2O, to draw it, if you can count your electrons. So we have 4 valence plus 2 plus 6. So we'd have 12. Again, I'm showing my math to make sure you remember how to do this. You can also do, I'll do a hydrogen, another hydrogen. Sorry, let me give myself more space. And carbon, hydrogen, and the oxygen. And then you would do your octet, and you would count 2, 4, 6, 8, 10, 12. You've run out of electrons, so you have to share 2, and that's what we have. So that carbon is, again, a planar triangle, 120 degrees, and it's sp2. So same answers as over there. How many sigma, how many pi? Well, there's 3 sigma and 1 pi. Again, you can make the pie whatever you want. Pecan pie, maybe? I went to a wedding and got to sit next to the pecan princess, so maybe that's where I got my crown from. So I learned all about pecans. It's actually very fascinating. Yeah, they have a shaker to shake the tree, and that's how we get the nuts out of the tree now. All right, we're gonna do one more, 2 more. C2H2. I'm gonna erase this one. Now you're going, yeah, that whole other board, but it's so clean. I'm saving it for the next page. So C2H2. So you can count your electrons. You have 2 times 4 plus 2 more, which is 10. You put the carbons there, put 1 hydrogen on each carbon, and whatever you try to do, carbons are gonna have to make 4 bonds. You're gonna have to share. That is 2, 4, 6, 8, 10. So we have a triple bond. This one also is our linear 180 degrees. So we can actually see how I drew it, 180 degrees. And the hybridization would be sp because each carbon only has 2 clouds around it. So if I look at this carbon over here, it has a hydrogen, and then this would be its other cloud. Sigma and pi bonds. 3 sigma, 2 pi. So a triple bond allows overlap. The sigma bond is the overlap in between the carbons. It's a very secure bond because it's in between the nuclei. And then the first pi bond between the carbons is above and below. It's an overlap of that y p orbitals, and the other one would be in front and behind. And so we're making like a double donut around that middle bond. So triple bonds, of course, are going to be much stronger, but they are much more susceptible to, they're going to be very reactive and susceptible to free radicals, which we'll talk about. Let's see. All right, the other thing I want to mention before I erase these two, both of these that I have here, still up there, that are only made up of carbons and hydrogens, are nonpolar. The middle one on your set, which had the oxygen, remember, is really greedy. It's going to take electrons, and so your oxygen, the CH2O, is going to be polar. There's going to be a pool, so there's our polar bear. He's going to high-five us. I'll do one more on this page, which is CH3CO2H. And I wanted to do this because we're going to be getting into organic chemistry, as I mentioned. And I don't want you to be afraid of, you hear all these things and, oh, what do I do? What do I do with all this? But this is trying to tell you what's happened. That this is saying these 3 hydrogens are on the carbon. So we draw the carbon, we draw the 3 hydrogens around, and then we have another carbon. Carbons love to bond to each other. And then there's going to be 2 oxygens and a hydrogen. Now don't do this. This makes no sense at all. First of all, the carbon wants 4 bonds. The oxygens really don't like being like that, strung out. So what's going to happen is we're going to have to double bond one of the oxygens. And then we have an OH. And so this is a carboxylic acid. This is acetic acid, which is in vinegar. And if you counted your electrons, which you can put your dots on your oxygen. Organic chemistry, we don't show the dots. It's a structural formula. But we're going to go ahead and describe this. And your homework this week, what you guys are going to usually see is these kind of pictures, like what comes up on the next page, and be able to describe them. So my carbon on the left, carbon number 1, that is a tetrahedral. Now what I've learned is a handful of you look at this and go, absolutely, that's a tetrahedral, and this one's a planar triangle. And the other handful of you say, what? Again, kind of look at one carbon at a time. 4 single bonds. Whenever you have 4 single bonds around the carbon, it's a tetrahedral. So it would be 109, and now we will also say sp3. This carbon, it only has 3 things around it. So the double bond only counts once. When you're counting electrons, of course, you count each one, but when you're doing this part, you only count it one time. So planar triangle, 120 degrees, and that is sp2. Because triangle is 3 things, so the s orbital and 2 p orbitals. There isn't a number hybridized p orbital, and that's what's going to allow that pi bond. All right, we're going to do one more, which is this oxygen. It is a tetrahedral also. It's a tetrahedral bent. So I didn't show the bend, how I drew it. I did that on purpose because a lot of times they don't show the bend. Oxygens love to have that kick, that bend, like water molecule does. And my water molecule, right? So we don't show the lone pairs, but they're there, and those lone pairs push the hydrogens down and make water that marvelous molecule that it is. All right, 2 more questions. So, how many sigma, how many pi? Pi's easy. One easy as pi, right? Maybe it came. Maybe Linus Pauling came up with that comment. Easy as pi. sigma. I got 7. So there's 4, 5, 6, 7. So there are 7 sigma. All right. Mama Polar Bear wants me to ask the question, hydrophilic or hydrophobic, or polar or non-polar? This is polar. That's why Mama Polar Bear is very happy. She's excited. The oxygens are going to be pulling that way. So if we wanted to show the polarity, it is polar. When we see the NOF, nitrogen, oxygen, or fluorine, we're going to have a pool. And great. All right. So if you have your notes, go ahead and turn the page, and we're going to look at a whole bunch of molecules. And we're going to count sigma and pi bonds in each of these. So I'm going to move us over to a nice clean board. And I'm going to draw our molecules, but you guys do this. Let me find my center. Just put pieces of tape so I know where to move it. How are you all doing, by the way? I hope you're doing wonderfully. So I'm teaching here. I imagine you each, I could put, a stuffed animal in each of your places, Nick and Leo and stuff. But they're just hanging. They're chilling. I don't know why there's a question mark next to the nitrogen on this page. That happens. Bill Gates and I struggle sometimes with his program. All right. Oh, it's no H. This page is also inspired by a couple of you and many over the years, because you do need to pick a topic. And so the lectures have suggestions throughout. And I'm actually, so I was walking here, thinking about the free radicals. It's not on the next page. I think it is. Oh, it is. I make a little video thing that is optional for you to watch, but I usually show it to my students because I get annoyed at some point. I can't get annoyed at you guys. All I can do is keep sending you love. All right. So if you're trying to draw these out, you can, or you can just say, you know what, I'm going to pull it up, and you can pause me as I draw them. I don't know how to pause my video. Let's go ahead and do these first 2 together, and then I'll go next one. So there's pictures to go with it. This is cinnamon aldehyde. So this is what makes cinnamon taste so amazing. And if you love cinnamon, like I love cinnamon, vanilla, all the spices, turmeric, they all have a molecule in them that is the wonder part. Now, isolating the molecule, you're gonna find research about how they did that, and then they give high doses of it, and it can do something, but we're not gonna prescribe it yet. But for thousands and thousands and thousands of years, cinnamon's been used medicinally as the whole cinnamon. Actually, all the parts of the cinnamon tree are used in Chinese medicine. It's the second herb you learn about. And they actually are finding in most of this research that you have to have things as the whole spice. And it actually has a bigger effect than when they isolate that one part out of it. So something to keep in mind. All right, the top one is an amino acid. This is an amino group, this is an acid group, beyond what you need to know for the class, but it is alanine. And a lot of people who are into bodybuilding feel they need to take alanine, so then they can't itch their chin or whatever the cartoon is. But I've had people pick amino acids or different things like that. There's also a special amino acid that's only found in green tea. I think it's called threonine. And there's actually other molecules that are amazing that are found in tea. So your topic wouldn't be tea, but you could pick the molecule from that. Same like caffeine. There's an amazing molecule in chocolate. So if you're really into chocolate, you can pick that as your molecule, trying to give you some ideas. And there's some more at the bottom of the page. All right, what we are doing is sigma and pi bonds. Just talking, so you guys can do your sigma and pi bonds. And then we're going to do hybridizations. And then we're going to look at polarity. Because Mama Polar Bear's over here to help us. All right, so this is a double bond. I don't know if you can see it. That's a double bond. So I have one pi bond. Again, pick your favorite pie. Pumpkin pie. Oh, I should teach this class in the fall. So we could talk about pumpkin pie, sweet potato pie. I should make that, see if Joey will eat it. Joey does not like sweet potatoes, and I absolutely love them. All right, so let's count our sigma. 1, 2, 3. All right, I wrote this one like this on purpose. Each one of those hydrogens is a sigma, and this hydrogen's a sigma, so don't forget them. And this is gonna be really tough because I'm gonna have to count them because I don't have one of you, I don't have like 10 of you yelling the answer out to me. And once I hear the same number enough times, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, I'm going with 12. It is 12. This is perfect opportunity for those of you who are new to me. A whole bunch of you signed up for the class suddenly the other day when I was in here doing my first week lecture. So I don't know where you came from. I'm assuming you came from the wait list for the other class. But I am human. I know I wore my princess, so you might think, oh, she's a princess. Oh. And why is she wearing those rose-colored glasses? Because I see everything as roses. Jessica actually inspired me. I'm pointing to where people sit in the class, so let's see. I make mistakes, so if I get a mistake here, somebody can email me and I'll send out what my typo was in my video for whoever watches my video. I came in twice this week and had to re-videotape, and I've let go of it now. I'm just gonna accept. I'm gonna make a mistake. You guys are perfect, I'm sure, right? Nobody is. Why we're here in this human experience, to be here now so that we can take that next step. All right, hybridization. The carbon, these carbons are both tetrahedrals, and this carbon, circle it, put a star. The starred carbon is the triangle planar. 120 degrees, sp2. Actually, all I wanted was the hybridization. The other two carbons were sp3. And then a side note, the nitrogen is actually also sp3. And I want to mention again, this is a lot of what you're going to see is structural formulas. They don't show those lone pairs, but that's what I talked about at the very beginning of this lecture. All right. Polarity. Oh, definitely there's a pool. We see NOF, we see nitrogen, oxygen, and fluorine. So the oxygen's pulling more than the nitrogen. They're both going to be pulling, but the oxygen, the most polar thing is the OH. If you see a fluorine, you're going for fluorine, but we're not going to see fluorine. These are magnificent organic molecules. If you see an OH, OHs are special. It's why water is so special. Pick the OH. This is the most polar. All right, on the next one, cinnamon. Love cinnamon. This is our polar bond. But overall, it is hydrophobic. And this is a tough question, but I think I asked this question. There is a ratio of carbons to oxygen. So if you get more than 6 carbons, you lose the polarity, the attraction to water. So we do have a polar bond, but all of these carbons make it hydrophobic. So hydrophobic means water-fearing. I do not remember what I talked about, and I don't have you all to tell me what I talked about. So it's water-fearing. This one up here is polar, and so we say it's hydrophilic. And so it loves water. So Philadelphia, so for Cabri, a shout out to you. Philadelphia is called Philadelphia because it is the city of brotherly love. And so Cabri and myself also, I've been to Philadelphia and gone to see the beautiful statue of love that's in the center of the city. And it's a beautiful, wonderful statue. And you know, we'll send love out to people there on the East Coast, because we're very blessed here at this point. And we will continue to keep sending good vibes. My whole family's, actually not my whole family, most of my family's on the East Coast. And so I think of them constantly. All right. You can go, no, don't erase yet, but you can always rewind if you had to go back and grab some note there. All right, we're doing the next two, so if you have your notes, you can go ahead and count. Or you're gonna copy this down. So you're doing your sigma and pi, your hybridizations, and your polarity. And let me draw our last one. Okay, I have to tell you, something came up, a friend, former student, Eekbert, remember Eekbert and the three gnomes, if you're in my class last term, she came up with the name nomenclature for my YouTube channel. So my son put it in last night. I went to look at it this morning and I was like, actually horrified, because somebody else had come up with that name. And then Eekbert said chemistry. Instead of just chemistry, put it as a Y, and so it's like chemistry. Oh, but some beautiful gentleman over in India who probably has been teaching chemistry 100 years longer than me or something, he actually already had a website named that. So I think I should have a contest, and one of you guys come up with a name for our YouTube channel. Well, I guess it's mine, but it's really all of ours, because I made it for you guys. It's like an early birthday present. I forgot to ask. Is anybody's birthday this term, this month? Joey's birthday is the day before Easter. So, yeah. 22 years ago, I would have been like, you would have all been watching the video going, is she gonna like go into labor in the video? But it was 22 years ago. All right, these two are really awesome. So again, trying to inspire. And so I am not gonna pick a topic for you, because your topic is gonna gravitate to you, what you're interested in. I am interested in health and eating whole food, plant-based. And so broccoli, this is the power food of broccoli, love broccoli, and it is sulforaphane that is in it. And so if you want to go in, there's so much research you could find on it, because you all have to have two, I call it peer-reviewed research papers, but scientific research that you talk about, a good solid paragraph talking about it. And then the one at the bottom, this is GABA. This was that bonus question on the very first email that I sent out. And so GABA is a neurotransmitter that calms your brain. So when you meditate, there is these 10 molecules of meditation. Actually, there's 1,000 million of them. But when you meditate, you feel calmer once you learn how to. And most people have trouble meditating because they're like, there's all this chatter going on in my brain. And so GABA is a calming, and it evens out the chatter. And eventually you sit down to meditate and your body just releases the GABA. It must, if we're thinking that we're molecular beings. And it helps to cut out the chatter. And you just go into this beautiful, blissful place. It's going to be an extra credit for you guys to meditate. I think I talked about it. And you just focus on your heart. Just breathe. Don't think about the words. Think about your heart. See if you can even feel your heartbeat. The lub-dub. Was that first sound you heard? Was the lub-dub. Not your own heart. It's the mother's heart. And yeah. And you send out love. So after you get to your heart, send yourself love. Embrace yourself. But then you want to send it out to everyone. Those people in Philadelphia. Send it to the people in Philadelphia and New York and all around this beautiful planet, because we are all one. So the second one, this was awesome. I found this picture online. So these two are very related. And so the second one is found in magic mushrooms. And So last year I did a talk for students, and I'm going to make it and post it, and it was on the molecules of meditation because I was perturbed at them because nobody had picked a topic, and it was week 7. And I'm like, come on, somebody has to pick a topic. So I did this PowerPoint for them, and they all sat and listened to it. And I'll let you know, after I got done, it was like, 9 o'clock, I'd gone over again. They didn't all leave. Half of them left, but half of them came up and stood in this nice lineup here, and they all had topics. And I was so excited because I thought they were going to pick like GABA and things like that. Oh no, they all picked psychedelics, a different psychedelic. We had every psychedelic was talked about last year. There are a lot of them. And actually, the thing I will tell you is there's some really cool research that's been done. And so then when I went on my silent retreat, just got the one silent retreat I was going to go on this term just got canceled for obvious reasons. But when I went on my silent retreat, I told my teacher the story how it was her trying to say the word anandamide during a lecture, which is the number 1 molecule of meditation. And yeah, that everybody, I talked about the molecules of meditation, and they all instead picked psychedelics, which, you'll have a vision and stuff, but it's not actually, is it real? Is anything real? Go back to that. All right, so back to broccoli. Yeah, and I'll have other ideas. You can pick plastic. There are so many. Kevlar, actually, really cool would be silk, because there are these, this type of silk from some spider, and it's stronger than Kevlar and much, much lighter. And so they are making, starting to make those bulletproof vests. But hopefully there won't be a need for them. The problem is the spiders fight with each other, and so they can't farm them. And so they're doing really weird things to try to get this way to make the silk in other things. Like for real, if you're like really bored and into this stuff, somebody spliced it into goats and you can milk the silk out of a goat. I did not go and look at the picture. Some of my students, when I talked about it last year, they went and Googled it and they said it's really bizarre. All right, did you guys finish all the questions? I was just like giving you a chance. All right, so pie is easy. Easy as pie. 1, 2, 3. You know what? When we do our potluck in June, when we all come back together, why don't we just do a pie potluck? We'll all make a pie. Do you know how that would be crazy? Because we'd all be like the first 10, 5, 6 talks, everybody'd be like, oh, that was awesome, because we're all going to be jacked up. And then by the 7th talk, we'd all have crashed. So you're not going to all make pie. But we could spread it out over a couple days. Go make pie now and take a picture of your pie, homemade from scratch, and send me a picture of it. Maybe I'll give you a bonus point. All right. Maybe a broccoli pie. Oh, I did this on purpose. I remember doing this because I need to teach you how to look at these molecules, because a lot of you are going to now pick molecules. So the previous ones showed the carbons. These are not. So every corner, every line that is not coming off carbon, that's coming off the sulfur, every corner in the zigzag, those are carbons. I mentioned this to some class. All right, now we have to add hydrogens. Carbons make 4 bonds. This carbon has 4. Sulfur is right under oxygen, so it's going to behave like oxygen, 2 bonds. Nitrogen, 3. So nitrogen's good. My sulfur here, holy moly, that's probably why this is such an amazing thing. That sulfur does have 4. You can do that because that's its octet. But this is a carbon, and so this carbon would have 3 hydrogens coming off of it. So hydrogen, hydrogen, hydrogen. This carbon needs 2 more bonds, so those are hydrogens. Now, what I find on homework, on your worksheet and stuff, a lot of students will draw these in, and that helps them to see it. But this is a shorthand way of drawing, and the organic chemistry lab that I'm going to be videotaping next week, we'll talk about that. And you'll become very proficient at it because you will see these on your midterm, and so you'll need to be able to count them on your own. All right, so how many sigma bonds? So the picture did show 1, 2, 3, 4, 5, 6, 7, 8, 9. But then we have to add in all those hydrogen. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have a total of 20 sigma bonds. So most of you probably counted 9, unless you knew that trick that I was going to show you. All right, hybridization. All these carbons in the zigzag, those were carbons. They are all tetrahedrals, sp3. Actually, let's just write it over here. These are all sp3. If I asked you about the sulfur, it has 1, 2, 3. This is an sp2. If I asked about the nitrogen, it only has 2 things around it, sp, sp. Carbon also has 2 things around it. And they can do that because they have an unhybridized p orbital is what's happening there. All right, nitrogen's other unhybridized p orbital would be where its lone pair of electrons would be. Polar. Oh yeah, we got pooling. The nitrogen's pooling. Sulfurs are also going to be pooling. Oh, and we have that oxygen. It's the most polar bond. I'm going to bet it's the sulfur oxygen. So let's just go with that. And there is a lot of things on this that can pull the sulfur, the nitrogen. And so I'm going to go with this is hydrophilic. So we'll just put a heart for hydrophilic. And in fact, these guys down here, just looking at them, I see O's and nitrogen all over, so they're both hydrophilic. And if I asked you most polar, oh, the oxygens. To me, it doesn't matter which oxygen part, but oxygens are going to have polarity. Now, something else that's in my email, in your body ionizes acids. So the acid that we had drawn over here, if this was in your body, it would have lost that hydrogen. That's something you do not need to know, and is something that drives me crazy because most textbooks do not show it correctly, except for biochemistry textbooks. I don't know why people are afraid of ions. But GABA is carbon. If you want, you can write it in at every corner. And then you can draw your hydrogens if they need it. The nitrogen has 4 bonds. That's why it has a plus. So when nitrogen makes an extra bond, that 4th bond, it will end up with a positive sign. And so basically it's sharing those 2 lone electrons. This oxygen, this is a negative. It lost a bond there, and so that's why it has a negative. This oxygen has 2 bonds. All right, this carbon. And what this is trying to show you is what really happens in organic molecules. We draw them as if they're straight out like that, but single bonds are always rotating around. And so if GABA rotates like this is how it fits into its receptor. And magic mushroom molecule here fits beautifully into that receptor because it looks just like it. All right, but you should not do drugs. I've never done it. So you shouldn't either. All right, there we go. But how many pi? 1 pi. And how many sigma? So you can count your lines first. 1, 2, 3, 4, 5, 6. And now you can count all your hydrogens. So 3, 4, 5, 6, 7, 8, 9. So 6 plus 9 is 15. So we have 15 sigma. That's how I go about it. So we can check. 6. All right. And it is definitely polar. There's my pool. It is hydrophilic. Hybridization. These guys are all tetrahedrals. So over here, we're all sp3s. This one is an sp2. All right. And so over here, we run into an interesting thing. And I wanted to show you a cyclose. So those are carbons. They would be sp3 because they have 4 bonds. So this carbon here, it's part of the ring, as is this one. And so this carbon actually has 1, 2, 3 bonds. So it's just going to have 1 hydrogen. And this one is going to have 2. So I'll draw 1 on each side. The nitrogen has its 3 bonds. The oxygen has its 2 bonds. The hybridization, we would still say it's sp3. The bond angle would have changed because it would have to be the bond angle of a pentagon. which is pretty close to 109. I think it's 108, but I don't remember off the top of my head. All right, it's polar. The oxygen is going to be pooling the most. Everything over here is sp3. The nitrogen, it would have a lone pair, so it would be sp2. And I think that's it for that page. All right, we're going to do one more page, and then we'll move on. There's my eraser. It's always on the floor. And I want to do this page because this page has to do with valence bond theory. You guys can stop me and go back and whatever you want. If you need a break, we can keep going or making a bunch of little videos. Last week I was trying to figure out how to do it. Oh, this page. We're going to be talking about bond order. I mentioned this very briefly last week, maybe. Again, I had to remake the video, and I don't remember if I cut this part out. So let's just do it with an example. So we need Lewis structures for each of these. So count your electrons and make your Lewis structures. So pause me, draw your Lewis structures, and then you can start me up again. Those are my electrons. My tiara keeps falling off. My head is too big for itself, apparently. You will end up in the SO2 with one double bond. It is a resonance because the double bond could have been on the left or right, and bond order helps to explain this. In SO3, if you're going, what? How did you get that? I told you to stop me and do it yourself in class. Would have had a chance to breathe. This is also a resonance. SO3 -2 though, because of those two extra electrons, it does not have to, we can show the oxygens any way we want. It does have its, those extra 2 electrons are there. It is not a resonance. And a reminder, if you ever remember to show a bracket with a -2, that's awesome. I remembered. I'm so thrilled. All right, let's actually, before we do bond order, let's talk about these guys are planar triangle. These first two, this would be a planar triangle bent, so they would be sp2. This would be a tetrahedral pyramid because of this lone pair, so it would be an sp3. But what we're going to do is bond order, and there are different definitions of it. My definition, they all mean the same thing. My brain really simplifies things. It's the average bond. And it is always the same between the same types of atoms. So if we're comparing, these are all sulfur-oxygen bonds, so we can compare it. You can't compare a sulfur-oxygen to, say, a carbon-carbon bond, because there's going to be different nuances because of the sizes of the atoms also. But this is the average bond. So you can just look at it. If I have a single and a double, the average is 1.5. Or here, if they're all singles, my bond order would be 1. The way you can calculate it, and again, the way I do it, is I take the number of bonds, lines, divided by the number of linkages or outer atoms. And you can look in the book or Google and you can get a different definition, but you get the same answer. So 1, 2, 3 lines, 2 outer atoms. So 3 divided by 2 is 1.5. If I ask you what's a bond order, I don't care if you do a fraction or you do it as a decimal. They're the same number. Right here, 1, 2, 3, 4. And we would divide by 1, 2, 3. So 4/3. Resonances are going to give you fractional bond orders. And if they're all single, this would be 3 divided by 3, which you would, of course, reduce to 1. And this one, if you want, you can say 4 divided by 3. You can do it in a calculator. It is 1.33333333. So we have 1.5, 1.33, and 1. That is the idea of bond order. And so we're going to compare them. The higher the bond order, as you increase the bond order, you are going to increase the bond strength. You know what's great? I can write really low on the board, and you can all see me because this desk isn't in the way. See all the weird faces I make to myself also. It's been very humbling. You decrease the bond length. So an inverse relationship. So as you increase the bond order, the mantra we usually say is it becomes stronger and shorter. And I did it under this one because it was the highest of the three. So the question would ask, which is the shortest? You would say SO2. If I asked which is the longest, you would say the sulfite. And then the strongest would be the SO2, and the weakest would be over here. So that's the idea of bond order. Not so bad. All right, let's go back and do isomers. Again, having those boards that just you push a button and the whole thing erases, they're awesome. My handwriting is terrible, Anna. So you're seeing me being like really self-conscious. You're gonna be a total goofball and videotape it, and how bad my handwriting was. It's really hard to do Lewis structures on those smart pads. All right, so we're gonna look at isomers, and I made these for you today. C2H4Cl2 and C2H2Cl2. So carbons are going to be in the center. Oh no! It's like the princess and the pea. All right, I lost my crown. The carbons hook up to each other, and then we're going to put 2 hydrogens on each one. I did this one, I think, the other day. Don't remember if I erased it. And 1 chlorine on each one. And count your electrons. They're going to both have 26. And an isomer, this is an isomer. I would have to put the chlorines on the same carbon. And I wanted to show you something that happens that is incorrect with this one. So this is single bonds. This is sp3. And it's a question that comes up all the time. Why couldn't you do this as an isomer? I'm going to leave the dots off just for time. That why can't you just rotate the well, why is this wrong? And it has to do with this is a sigma bond, and a sigma bond rotates. So the chlorine on the bottom or the top is the same thing, but moving both chlorines there, you'd actually have to break things. And so I made this. So we can just actually, the single bond freely rotates. I know it's just a model, but it freely rotates. And so up, down, all these positions are equivalent on a tetrahedral. This would be something different because both chlorines, both green balls ended up on the same carbon. So I actually had to pull it off, put it on a different one. Also a reminder, they are both polar, high five, nose bun for Mama Bear. So the chlorines, oh, that's some yucky chalk, sorry. So the chlorines would be pulling, or in this case, the chlorines would be pulling there. Now, the reason I wanted to do this is I wanted to talk about this one. If you give each one a hydrogen, and you give each one a chlorine, you're going to end up having a double bond, so the carbons have their 4. And to show this nicer, actually you can do, it's going to come out at angles. Because of the double bond, you put your dots around your chlorine, which you would do for things you're submitting, the worksheets, your lab, of course your exam. All right. This has extra isomer, which is you could put the chlorines across from each other, and of course it has the one where both chlorines are on one side. do exist as isomers, and it has to do with if you have a pi bond, so we have 1 sigma and 1 pi, the pi bond, there is never ever rotates, no rotation. So it's stuck in place. It doesn't move. And so our sweet little models, here's my double bond. You know, I've tried to show this to students and rotate, and I've broken so many of these. But remember the overlap. You have 4 electrons in there, so 2 of them are in between the carbons and 2 are above and below, and that does not allow free rotation, that pi bond, because of the overlap, is above and below, and so the carbon can't rotate. And so you do get 2 different ones. Now, this one over here, I already showed you, we have the pull towards the chlorines. One of these is nonpolar. And that is this one down here. It is actually nonpolar. Polar bears, like, yes, she got it right. This one is polar. The chlorines are both pulling up. But here, these chlorines would be across from each other. And this is actually called cis and trans. I'll be talking about that when we do the organic lab. But cis is, in nature, you find things as cis, trans. It does change properties. My understanding is rubber is cis, and all they did was, if they heat it up and allow it to come back together, it will come back as trans, and the covering of a golf ball is the same molecule as trans. I don't know if I'm 100% sure on that, but I remember somebody telling me that like 20 some years ago. So if you want for an experiment, you can go out and kick your car tire or your bike tire, the rubber, and then you can go find a golf ball, and it is much harder, and that has to do with the shape that these make. So something I wanted to talk about with free radicals, just briefly. So, does anybody remember what a free radical is? You know, like I mentioned in my other class, so everyone does the healthy change. And then your class, like last term, actually 2 people did. Only 1 person wrote it up. I think somebody else was going to, but they're like, I don't need the points. It's not really about the points, you guys. It's about your life and about other people you love. And that was the thing that was really cool. All these people who made a healthy change, they ended up having the other people in their life also made the healthy change after like a week or even just a few days. And a lot of them were parents, and they said it was like they were, everybody just like started gravitating towards them because of these changes they were making. But a free radical is an unpaired electron. And this can happen from many different things. And so there's this beautiful picture that I absolutely love. I put it on there because when you have free radicals, because from smoking, from pollution, from poor nutrition, and from stress is one of the biggest causes of free radicals. Your attitude. If you're going to think bad thoughts, you're going to get free radicals. If you're going to just think love and bliss and send love out to everyone, you're going to stay as healthy as can be. But you can't spell as well either. So apparently you spell aging in a very interesting way, but it causes a lot of our long-term diseases that are very prevalent in our society. And so I wanted to mention that because if you have all single bonds, they make a tetrahedral or an sp3. And these guys can stack. And we call this saturated. And we're going to talk about this when we get into organic chemistry. And I'm not going to stop and go back and edit because that's a lot of time. What I was going to get at is what we just did with the double bond is if you put a double bond in, and we'll talk about the cis-trans more in the organic lab, but if you suddenly have a double bond in here, a double bond does something. The overlap, because these are all sigma bonds, and the overlap, one of those most missed questions, the overlap is between the nuclei. So if the overlap is in between the nuclei, they're very safe. They're not going to get damaged when they're exposed to stuff. Where a free radical happens is whenever you have a double bond, whether it's cis or trans, that doesn't matter. And this happens because of how the overlap is. The overlap of a pi bond, so the sigma bond, you're in between, you're perfectly safe. The pi bond, you're like up above, you're on the head. It's like, that's what happened. My crown that popped up was like a free radical happened. So the pi bond, because of where the overlap is susceptible to free radical damming. So how can you knock an electron out? Well, if you get a photon of light, so that's where the UV light, so when the ozone isn't there, we get the UV light, can cause damage and knock an electron off. There's an electron, and now you have an unpaired electron. So now this bond is just 3 electrons, and this guy is not happy. It's going to go and try and take electrons. Where you have a lot of double bonds in your body is in your cell membranes. Your body is like trillions of cells and just loaded with cell membranes, and there's lots of double bonds. Double bonds give it wiggliness, and so they're very susceptible to damage. Another thing that does this, oxygen. Just breathing, because oxygen's so greedy, and it's sometimes every cell in your body goes through a process. Like your car's combustion engine, one step. Our body goes through several 30-some steps. And the last step is oxygen, which drives everything through your body in metabolism, is oxygen wanting an electron. And so sometimes it just gets overzealous, and it combines with the electrons and makes water. There's always hydrogens around. And sometimes it just combines incorrectly and ends up as a free radical. This guy. So it ends up as O2 with a negative, an extra electron. This is called superoxide. Has an oxidation state of -1/2. You actually have an enzyme in your body. We were created with this enzyme called Superoxide Dismutase, so SOD. And when I was in graduate school, Dr. Friedovich, not Friedo, but Friedovich was called Dr. SOD, because that's what he did his research on. Nicest guy. So nice. He told stories, and somebody missed class one time and had to borrow his notes. Every class he had these stories, and in his notes they said, were the stories. He'd have, tell a story about this, and so I thought that was funny. I have nothing on my notes. They're kind of blank. Hopefully yours are not blank, but you're filling out your notes. All right. So oxygen, we have to breathe, but this is the thing. There's like all these YouTube things right now about breathing through your nose. It's so important because you breathe slower. It has to slow down your breathing. And that's, again, where meditation, you learn how to breathe slower and deeper. And so your exposure to oxygen. There are the people who over-work out, over-exercise, and they end up having more free radical damage. It was something in that air, and it was that place in Arizona, down by Tucson, Arizona, where they built the biodome. And that was one of the things they found is they figured out the minimum amount of food they need to eat and exercise. That oxidative stress ended up being one of the biggest issues they had. Sorry, I'm trying to think of the other two. One is, those transition elements, so like iron and copper and stuff, we absolutely need it. But iron, because it can go between the 2 and the 3, +2 and +3, it can steal an electron. And so this is one of the things, women don't tend to have heart attacks, really, until after menopause. And that's because we have a monthly flushing of iron from our body, so we naturally have usually lower iron levels during our reproductive years. And there's one more, and it is heat. So high temperature. High temperature will jiggle it enough, so jiggle, 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 and it knocks it off, knocks an electron off. So when you cook food that has double bonds, which is your oils, and you use high heat, so frying with oil. Oil is highly processed, so it's already been oxidized, but then you cook with oil. I don't actually cook with oil, which 3 years ago when I first heard this, I'm like, it's impossible. You cannot make a curry without oil. You can make freaking amazing stuff without oil. you cook with either just water or broth. I make my own broth, and it actually comes out amazing, even better, and you feel great about it because it's water-based. And you just have to kind of have everything chopped up first. But back to that broccoli thing, if you have broccoli cut up and you wait 20 minutes, it actually makes the broccoli, that sulforaphane, the molecule before it, is what's in broccoli until it gets chopped or chewed. But to make the step to make the sulforaphane, you need an enzyme to do it, and when you cook, you destroy the enzyme. But if you chop, the enzyme will be active, so you're supposed to like chop your food and wait 20 minutes before. And so if you need a sous chef, so you have to get everything prepared, kind of like in those cooking shows where everything's ready for you. You go meditate for 10 minutes and love out to everybody, and then come back and you can cook. All right, I will see you at the next video. Bye-bye.